Hello, everybody, and welcome to Astronomy on Tap Charlottesville. This is the 12th Astronomy on Tap Charlottesville event we've been able to have, and I guess the fourth one we've been able to have virtually. And so we're really excited to be able to post another event for you guys and to see some people in the chat for sure. So tonight's going to be a really fun night. We have some great speakers. We're going to lead off with we're going to lead off with Geoff Chester, aka Starry Eye Guy. He's going to be talking to us about astrophotography. Then we're going to dive into Dr. Rachael Beaton's talk on the Hubble Constant and the expansion of the universe. And we're going to wrap up the night with Dr. Wes Rile. Finally, Ed Murphy's going to have a couple of segments in between some of the talks. On astronomy and the news and on what's up in the night sky. And as always, I am your host. I am Matthew Ryle, aka Dr. Buzz Lightyear. And I am going to be the MC for the event and lead us through all of the awesome astronomy content that we have for you guys tonight. And so as usual, just like to give an introduction to what Astronomy on Tap is and what Astronomy on Tap Charlottesville is to those that might be new viewers. Or for those of you that just like hearing my voice. And so Astronomy on Tap Charlottesville was founded by UVA graduate students in October of 2018. And the whole purpose was to bring astronomy to the Charlottesville community in a sort of fun and relaxed setting. And so pre-pandemic, we would have events at local bars, as you can see right here. They were oftentimes, the rooms were packed to the brim with about 100 people attending those events. And we're definitely going to be continuing those when we are able to do so in the Charlottesville community. But one of the greatest things about the pandemic has been the ability to be able to reach people beyond just Charlottesville and do fun astronomy on content for those outside the Charlottesville community and bring people into our Astronomy on Tap Charlottesville family. And so if you want to check us out, make sure to like us on Facebook. You can find the Facebook event link there. And I think Catherine might be able to link that into the chat for people. If you want to be able to click on that to see all the other cool stuff that we have going on in Astronomy on Tap Charlottesville. And so our schedule for today is as follows. We're going to be starting with Geoff Chester. He's going to give us a nice talk on astrophotography. Then we're going to be jumping into an astronomy in the news segment with Ed Murphy. And then we're going to have a talk by Rachael Beaton on the Hubble Constant. Then as usual, we always have astronomy trivia throughout the event. And so we have that today as well. There's going to be some fun astronomy, some spring-themed astronomy trivia that was done by Jacob White. And then Ed Murphy's going to be doing another segment on what's up in the night sky, what fun things you might be able to see in the night sky this month or the next month. And then we're going to wrap up the night with Wes Rile, where he's going to be talking about binary stars and the role of binaries. And so these are what each of the individual talks are going to look like. Some of the posters that you guys might have seen if you follow us on Twitter or on Facebook. As usual, and as always, since we've started these virtual events, we've liked to collect donations to various Charlottesville community members. And in particular, the one that we're doing tonight has to do in part because this is kind of like the anniversary of when we had to start doing the 1-year anniversary of when we had to start doing virtual events because of the COVID-19 pandemic. And so the Charlottesville Area Community Fund, what it does is it provides resources to organizers and organizations in the Central Virginia area to help alleviate the effects of COVID-19. And so we're starting to now see the light at the end of the tunnel. This is our time to be able to donate as much money as you possibly can. Any little bit helps to help out the Charlottesville community and sort of overcome the effects that this pandemic has had. And so this fund operates with government, local government, schools, and the private sector to help various emerging needs in the community. And so that's also been linked in the chat. You can check out that link to be able to donate money to the Charlottesville Area Community Fund. Additionally, throughout all of the talks, you guys are going to be able to ask questions to all of the panelists that come up. You're going to be able to chat with Buzz Lightyear himself. And you can ask any questions or chats with the Q&A feature right here. So if you have any questions, make sure to ask it in the Q&A feature. And additionally, you can chat to the speakers, but you're not going to be able to chat to other viewers, just so you guys know. But I will be checking out the chat in my other window that I have here. If anybody has any fun, nice things to say to me, it's always great to just see a hello or something like that. And yeah, I'm more than happy to keep this discussion, this fun discussion of astronomy going. But as usual, we like to start the event by knowing who's watching, right? This is an Astronomy on Tap Charlottesville family. We're inviting as many people into the family as we possibly can. And so I want to know who we have watching with us today. And so there's going to be a poll that pops up on the screen. I'd appreciate you guys to be able to fill out that poll. The first question we're asking is, where are you watching from? And so what I've popped on is from our last event, the 11th Astronomy on Tap Charlottesville event. That's sort of the audience that we had. We had a good amount of people, about 50% from Virginia or from the Charlottesville and Albemarle County community. But it's always great to see people tuning in from outside of Virginia or even outside of the US. And if you are one of those people from outside of Virginia or outside the US, you can go ahead and say it in the chat. It'd be cool to see where people are tuning in from. So if we've had people fill that out, Catherine, you can go ahead and make that available again. So it looks like, as usual, we have a good amount of people tuning in from Charlottesville or the Albemarle County region, but we do have a couple of people tuning in from outside of Virginia. So if anyone from outside of Virginia can throw into the chat, maybe I have some family of my own from Pennsylvania that might be tuning in. So that'd be pretty cool for sure. All right, question number 2. Let's keep learning about what you guys are doing tonight and how much fun you might be having. It is an Astronomy on Tap event, right? And so our next question is, what are you guys drinking tonight? I've just got a beer. I have Corona, ironically, I guess. And I'm going to be drinking that over the remainder of the night. So what are you guys drinking tonight? And this is what the audience that we had last time. We had a bunch of beer drinkers, which makes sense because when we were doing our events, we were typically having them at breweries or things like that. And so go ahead and fill that out in the poll. All right, Catherine, we can go ahead and make those results known if people were able to fill that out. It looks like we got water tonight. Maybe people are watching from outside. That's okay. I got some water with me as well. I'm not just going to be drinking beer all night. I got water too. So a combination of beer and water makes for a fun astronomy viewing experience for sure. All right, question number 3. What's your astronomy experience? And so we like to make these events as accessible to as many people as possible. The experts, people that have no astronomy experience at all. And it turns out our primary audience for the last one was just fanatics, which is great. And so what is your guys' astronomy experience? I am recently, I guess, a minted professional. So I would have to click professional since I just defended my thesis in December of 2020. And I've actually been teaching at UVA, a couple of classes at UVA today. Maybe some of my students are tuning in for tonight. I let them know about it in class, so that'd be fun. Although they'll be seeing me dressed as Buzz Lightyear, which maybe that's not so fun as well. So Catherine, you want to go ahead and show that? What we got? We got people tuning in from Austin, Texas. Awesome. Drinking a Victoria from Mexico. Nice. Good to see you. Thanks for joining. So most of our audience for today is a fan as well. About 43% of us. We got someone that has no astronomy experience as well. It's great to see you tuning in as well. Hopefully you guys have a nice, fun night. And final question, we always like to end it with a sort of fun one rather than just the getting to know you one. And that is, what is your favorite object to look at through a telescope? And so our choices here are the moon, the planets, nebulas, star clusters, or others. And if it's other, you might want to go ahead and tell me in chat. And so I think this is, I put this in here because I think this is my biggest hot take in astronomy, and that my favorite thing to look at through a telescope is probably the moon. I think the moon is the most underrated astronomy object out there. Even though we see it most nights, it's definitely one of the coolest objects to actually look at through a telescope with all the cool details you can see. So let's go ahead and see if some of you guys agree with me. Ooh, comets. Yeah, that would have been a good one to include there. I was actually able to, whoops, sorry about that. I was able to see the comet over this past summer, which was very cool. So let's see what our results are today. The planets. I'm guessing most people probably might be the planet Saturn. The first time I showed my parents Saturn through a telescope, they were convinced I had taped a little tiny sticker at the back of the telescope that they were looking at. So it's definitely a life sort of puts nice things into perspective when you look at some of the planets through the telescopes for sure. All right, M51, nice. Galaxies for sure. All right, so this actually leads into, that question leads very nicely into our first speaker of the night. And so our first speaker is going to be Geoff Chester, who's a public affairs officer and historian at the U.S. Naval Observatory. And he's going to be talking to us about astrophotography. And so Geoff's gone ahead and shown his video, which is great. So I want to just give a quick intro to Geoff before he takes it away. And so he's been working at the U.S. Naval Observatory for the past 25 years, and he's been providing tours to government and military officials, as well as the general public. And some notes on the U.S. Naval Observatory, for those of you guys not familiar with it, is that it's generally very important to your life, since it's the world's authority kind of on timekeeping in a lot of ways, celestial or atomic timekeeping. And it's vital for things like GPS and the internet. So the reason that we are able to talk with each other about astronomy via this webinar is thanks to the U.S. Naval Observatory. Now, before the Naval Observatory, Geoff worked at the Einstein Planetarium at the Air and Space Museum in DC. And additionally, he's a member of the Northern Virginia Astronomy Club, the Association of Lunar and Planetary Observers, and the International Dark Sky Association. And you can check out some of his work on Flickr or Facebook or Twitter about some of the pictures he might be showing you tonight. And so we're going to be linking that in the chat, hopefully, as well. And so I'm going to stop talking now and turn it over to you, Geoff.
All righty. Well, thank you, Matt. I appreciate it. Normally, I'd be wearing, normally I would be wearing this hat, my official U.S. Naval Observatory hat. But tonight, I'm going to be wearing this one here because this is the fun hat. This is the one that I really like wearing. And so one of the things that I have always enjoyed is taking photographs of places that I've been. That means that starting off at about age 12, I one night grabbed my dad's single lens reflex camera and kind of stuck it to the eyepiece of a telescope that I had. And I actually took a picture of the moon and I thought, hey, that's pretty cool. I'll probably never go there, but anyway, I've got a picture of a place that I'd want to go to. So over the years, I have done a lot of astrophotography. And one thing that I have learned in astrophotography is that you can spend an enormous amount of money pursuing photons with telescopes. But you don't necessarily have to, especially today, because things have revolutionized over the course of the last 20 years with the advent of essentially digital detectors, CCD and CMOS chips. So what I'd like to do is take you through a very brief, because I don't have much time, take you through a very brief history of, or very brief primer on astrophotography. And so let's see if we can get this thing to work. Okay, there we are. So that's who I am. There's my website. There's my, that's kind of my logo there on the website. In addition to working at the Naval Observatory, I'm also director, staff astronomer, and janitor for the Shoestring Observatory in Alexandria, Virginia, which is so named because I have to schlep my telescope out into the front yard underneath the street lights and then schlep it back in when I'm done. So it's a very, very kind of low-key operation. So astrophotography, one of those things that, you know, what I would really like to get is the kind of image that you see on the left. What I actually get is the image that you see on the right. And, you know, for all intents and purposes, that's not too bad. I can be happy with that. I can't remember how much money was invested to obtain the picture that is on the left, but I do know that I did not have to invest a small fortune to get the one on the right. Indeed, I managed to put 2 kids through college and still have enough left over so that I could pursue my other interests and amateur astronomy in particular. Every now and again, though, you do get lucky, and other people will sometimes see your work and decide, hey, that's pretty cool. So this was one of the first pictures that I ever took with a digital camera. Up until early 2000s, I was a dyed-in-the-wool film camera guy. And I had all kinds of elaborate equipment to hypersensitize film and just do all kinds of crazy stuff to, essentially get decent pictures of the sky. But I got a digital camera because, well, back in 2003, my wife sent me to Egypt for 10 days. Rather than lug all of my single lens reflex gear and lenses and bricks of film and tripods and stuff, I got a little point and shoot Canon digital SLR, or not even that, it was just a little point and shoot. And took that with me, and a couple of memory cards. And when I came back, I had the whole trip documented and found that this was really the way to go. So this picture was taken back in 2006. It records the launch of the first Minotaur rocket from Wallops Island, Virginia. And I consider this an astrophoto because there's the moon right up there. So today, it's amazing what you can do with one of these things. The basics of astrophotography revolve around a camera. This particular one here is one that I got about 10 years ago. I still use it as my primary astrophotography camera. It is pretty bare bones. You can pick one of these up used for probably less than $100. The only requirements that you need are that it has manual capability, so you can set your shutter speeds. You should have at least a 12 megapixel sensor, a self timer and or a remote shutter release, and you should be able to save images in the camera raw format. That's pretty much all you need to get started. A few other things. Obviously, the camera will probably come with lenses. Most lenses are designed for terrestrial imaging. And a lot of cameras these days come with zoom lenses. You can use zoom lenses pretty well, but the fixed focal length lenses generally have fewer lens elements in them, and so they can get you a little bit sharper star images. You want to turn your autofocus function off because the sensors in these generally use infrared, and infrared doesn't really focus well at infinity. So you want to use a manual focus capability. And a lot of these cameras now, they have a video preview mode that has zooms on it. So you can focus on a bright star or the moon or something like that. Use the zoom capability and get a really, really sharp focus, and then go from there. You'll also want to get a tripod. It's pretty difficult to handhold optics or cameras for more than a quarter of a second or so. So a tripod is a good idea. And you might want to get one that will hold about 4 kilograms or 9 pounds of payload. That should cover just about anything that you might have in a digital SLR kit. So here's a basic setup, pretty simple. That is my Canon T2i with a 24 millimeter fixed focal length lens sitting on a tripod. On the right, you can see an image that I made with that on a rafting trip that we took to Desolation Canyon in Utah in June of 2018. The foreground illumination is provided by the moon. The background illumination is, of course, the stars. And this is about a 30-second exposure made with the camera sitting on a tripod. This is kind of the basic way to start off. And you can actually get some pretty nice images this way. Here's one on the left that actually both of these were taken down on the northern neck of Virginia. The one on the left is looking out over a little side water called Mulberry Creek near Maratico, Virginia. And the one on the right is one that I got last year. I was really, really pleased to get this one with a very thin crescent moon, the planet Venus over here, and the planet Mercury up there. But there's one problem with a tripod and a fixed camera, and that is that the Earth rotates. Now, I will be honest and tell you that I took this picture back in 1985 at the Very Large Array out in Socorro, New Mexico, long before there were digital cameras, but nowadays you can take your slides and digitize them. And so that's what I did with this one. But there's this one problem that you have if you want to get nice long exposures, and that is that the Earth rotates. So we're looking up here. This is the star Polaris, which is very close to the North Celestial Pole. And you'll notice that over the course of this 20-minute exposure, the farther away you get from the pole, the longer the stars appear to trail out. So this can be a problem unless you want to do kind of artsy shots like this one here. Well, we have now technology which is really kind of cool. There are now on the market a number of these little star trackers, which you can basically pop your camera on. Some of them require electricity. The one that I have is actually one that has a little clockwork mechanism that you wind up. This is a really handy dandy and fun way to get into astrophotography. The basic idea behind it is that if you look over here, you'll see this little tube right there. You line that up so that you can sight the star Polaris through that tube. And then you turn a little knob here, which engages a little clockwork mechanism. And now you can track the sky for up to an hour. Now, generally speaking, your polar alignment isn't going to be all that good. So there's a general rule of thumb in how long you can make your exposure, and that depends on the focal length of the lens. For my 24mm lens, it's generally about 4 minutes or so. And the kinds of images that you can get with this are really pretty nice. This is comet Neowise, which was the comet that we had, the surprisingly bright comet that we had last summer, taken from down on the northern neck. Here's the Big Dipper over here for those of you who've been paying attention in the planetarium. And here's the comet over here. This was about a 1 minute exposure. Over here, I have a composite of several 3-minute exposures that were taken from the same location, just a slightly different perspective. And this is another interesting thing that you can do with a digital camera is you can get software that will allow you to stitch mosaics together out of different parts of the sky. So this is, I think, a pretty good example of just the kinds of things that you can do with this particular type of device. And this is one of my favorite ones here. I just got this one last month. Here is the constellation of Orion. There is Aldebaran, the Hyades, the Pleiades, and the planet Mars. And of course, since this was out in rural Northern Virginia on Turner Mountain out near the plains, of course, I got a plane flying away from Dulles Airport, but you know, you got to take what you can get. But some of you are saying, I want more. And if you're going to start getting into more sophisticated astrophotography, the first thing you got to do is get an adapter that will allow you to essentially hang your camera on the back of the telescope. And then you got to get a telescope. Now, telescopes today come in a variety of apertures. My favorite setup for most of the work that I do in astrophotography nowadays is this one here. This is a simple 4-inch refracting telescope on a Celestron AVX mount. And the beauty of these things today is that all you have to do is line it up on the pole, and then you can just use the hand control down here to point at whatever object you want to, and it will center in the eyepiece and away you go. Pretty interesting, pretty fun little setup, easily portable, goes with me just about anywhere that I can drive to. I have a slightly smaller version that actually folds up and allows me to take as carry-on baggage on a plane. But the basics are you don't need a humongous telescope in order to get some nice images. So here are a couple images of the moon. One of the beauties of digital imaging is that you can do something that was never possible with film, and that is what is called high dynamic range imaging. So you take a number of exposures that are 2 or 3 f-stops apart, and then utilizing software, you can composite those images together so that you can get an image that shows not only the brightly illuminated part of the moon, but you can also get the part of the moon that is in earth shine. And if you look at the close-up on this, you can actually see stars and other things in the background. But then you can also just take plain old snapshots of the moon. This one here is a color image. It's been stretched very slightly. You may notice there are some subtle color differences between the Maria here and the Mare regions in here. That's actually indicative of the geology that is prevalent in those particular areas. Now, recently, a new device has come on the market, and this thing is pretty cool. There are a number of people that are now manufacturing these. They're all based essentially on a Raspberry Pi computer. They have a wireless interface with Apple and Android phones and tablets. It will find and center target objects for you. It will assist you to get a very precise polar alignment. It controls the imaging camera and the telescope. It controls the guiding camera and corrects the tracking errors of your mounting. It stores images in your camera and or a USB stick that you can hang off the side of this thing. It literally makes deep sky imaging as easy as 1, 2, 3. Once you get it set up, you can command it to take a series of images and walk away for 2 hours, come back, and your images are saved, and you can then do some post-processing on them. So the kinds of objects that you can get are really pretty stunning. It wasn't all that long ago that to get images like this on film would require exposures, a single exposure of well over an hour. And you would need to manually use tracking on a guide star and a drive corrector to make sure your telescope stays centered on the object you want to photograph. That's all taken care of now by this new device. And who knows where it's going to go from here on in. The bottom line is, if you want to take if you want to dabble in astrophotography, there are a number of different ways that you can do it, a number of different ways that you can get involved, from simply sticking your camera on a tripod to bolting it to a telescope and seeing what's out there. So at this point, if anybody has any questions, I'm happy to entertain them.
Awesome. Thank you so much, Geoff. That was a great talk. Very awesome images too. That's so cool that you had a picture on the astronomy picture of the day. I've certainly seen that at some point and didn't recognize, of course, at the time that it was one of yours, because I definitely look at the astronomy picture of the day frequently. But anyway, so I'd like to mention to people that you could use the Q&A if you have any questions for Geoff. But I do have a couple of questions here. The first is in regards to the size of the telescope that you use when you got that attachment. So you used a 4-inch telescope, right? Was that right? The primary purpose of that? You wanted a telescope that you were able to, that was portable, that you can take places.
Yeah.
Or you know, have you used it with larger telescopes or things like that? You have any discussion about that?
Well, currently I own 5 telescopes. Each one has a different purpose. But for lunar and planetary imaging, actually, well, for lunar imaging and for deep sky imaging, the 4-inch telescope is really nice. It's easy to set up. It is it's got you know, the one thing, refracting telescopes generally will give you better images than reflecting telescopes. Now that's, you can get into all kinds of fights on the Cloudy Nights website about that. I also have an 8-inch and a 14-inch reflecting telescope. Those are used primarily for visual use when I want to go out and hunt down faint fuzzies by eye. And I also have a 9¼ inch Schmidt-Cassegrain telescope, which is my primary planetary imaging telescope. Now, I didn't get into planetary imaging because that tends to get a little bit more complicated. The 4-inch telescope, though, really does well. This picture that you see in the background now is one that I took with that telescope.
Oh, wow.
And, that's the Andromeda Galaxy. So that gives you an idea of the field of view that you get. I love being able to take images of wide fields in the sky.
Yeah.
One of the things that I find absolutely wonderful is to see, especially when you take an image along the plane of the Milky Way, just how many thousands and thousands of stars are out there, and they're just in our own galaxy. Here you have an opportunity to look through a pretty dense Milky Way star field, and then there's this whole other galaxy that's in the background. That, to me, is what it's all about. So the 4-inch telescope is probably the one that gets the most use. When the planets are around, then the 9¼ inch Schmidt-Cassegrain goes on the same mounting and sits in the yard and makes all the neighbors wonder just what's going on.
Nice. Cool. That's great. So in regards to one of the things that you had mentioned, then this tied into another question I had, is that what sort of communities would you recommend people looking out for that are interested in the astrophotography? Usually the way that from my sense is the way that people get the most into it is, they have someone like this to give a talk, and then they buy a camera, and then they keep, sort of a snowball effect that they get more and more into it because of the great communities of the astrophotography people out there. So I don't know if you
there's a large community on Facebook of astrophotographers. You can do a search on Facebook and you can probably find dozens of them. And they start off with people, we've had, I see postings there from people that have, taken an out of focus image of the moon through a telescope using a smartphone, and they'll say, okay, what do I have? And how do I make it better? And there are people there that will help you do that. You can actually get adapters now for your smartphone that will allow you to put them on the eyepiece of a small telescope, and you can take great pictures of the moon with that. I've seen some really amazing results that way.
One of the classes at UVA takes advantage of that, and that's with the telescopes we have. They have like the adapter connected to a smartphone that all the students obviously have.
But if you want to get into it in a way where you have a little bit more control and more flexibility in what you want to get, then I definitely would recommend picking up a secondhand DSLR. I was just thinking about one of the first times that I did deep sky astrophotography. I had spent, probably the better part of a week hypersensitizing a special kind of film that you could only get from Kodak, and loading it into my camera, putting that on the telescope, putting on a guide scope, and then I had my manual drive corrector, which had a little joystick, and it was like playing the world's most boring video game because you had to keep a star centered in the eyepiece of the tracking telescope for an hour.
It reminds me of some of my astronomy classes.
And you really, really had to make sure that you eliminated everything that could cause, who knows what. So I had been out there and I had been taking this exposure. I think it was trying to image the Horsehead Nebula in Orion. And I did this exposure for about an hour and everything was perfect. And I leaned back to stretch a little bit. And then for a brief second, I decided to just take one more look at the guiding eyepiece to see if my guide star was still there. And I bopped it with my glasses.
Oh, dang.
And there is an hour of my life that vanished into hyperspace. Well, the thing is you don't have to worry about that anymore because the exposure times, the quantum efficiency of CCDs and CMOS chips is anywhere from 50 to 80% of the photons that hit them are going to be recorded. The quantum efficiency of the best films that were available back 30 years ago was 3%. So your exposure times are much shorter. You can record much more detail, and you can get them in color. And if you don't like it, you don't have to worry about wasting film. Just erase it off your memory card and try it again. It really is the way that everything is being done now. And it's something that I think anybody who has an interest in the sky should be able to go out and take pictures of it and get really, really nice results.
Yeah, I'm definitely excited to take some of this stuff to try to get some of my own, especially with the stimulus checks that have come in. I've been considering trying to do stuff in regards to astrophotography. But anyway, unfortunately, we don't have any more time for questions. We do got to move on. But I imagine you'll be sticking around in the chat. If anybody has any questions, you're welcome to ask Geoff in the chat as well, and I'm sure he'd be happy to answer them.
Right. And here are some resources, which I think you're recording this so people can come back and look at it. I will also send you a PDF of the presentation if you want, and that has basically all the info on it.
Yeah, that'd be great. We're going to be posting it hopefully to YouTube, so for people to check out as well. So I can
cool
there as well.
All righty.
All right. Thank you so much.
It's been fun. Thanks a lot.
Yeah. All right, so I'm going to start taking over screen sharing capability. If you want to go ahead and stop sharing, Geoff. Let me see. Geoff, you got to make, yeah. Oh, there you go. Okay, we're good now. Okay. All right, so at this point, before we get diving into the next segment, I do want to have a quick discussion about the Charlottesville Astronomical Society. And that's because the Charlottesville Astronomical Society, or CAS, has been a great help towards Astronomy on Tap Charlottesville, helping us get speakers, helping us organize events. And so for anyone that's interested in astronomy, the Charlottesville Astronomical Society might be a great sort of group to join to do things like astrophotography or other sort of types of outreach events where you might just be looking at the night sky or hearing fun astronomy lectures. And so I'm pretty sure they meet monthly. Yeah, they hold monthly meetings, and they participate in many different outreach events, including star parties. And you can join or find out more at cvilleastro.com. So hopefully we can link that in the chat for anybody that's interested in joining the Charlottesville Astronomical Society. And I do want to give a special shout out. I'm not sure if he's watching today, but Scott Dureski is typically the one that gives the cast discussion at Astronomy on Tap Charlottesville events. But it is his birthday today. And so I decided to fill in for him so that he can celebrate his birthday. But happy birthday to you, Scott. And thanks for all the awesome help that you've provided both to me and to the Astronomy on Tap team, and then certainly to the Charlottesville Astronomical Society too. All right, so cool. So the next thing that we're actually going to be doing tonight is Ed Murphy is going to be taking over. So Dr. Ed Murphy, he is a professor at the University of Virginia, and he's going to be telling us all about what's going on in astronomy with an Astronomy in the News segment. So go ahead and take over, Dr. Murphy.
Thanks, Matt. Thank you very much. So welcome to Astronomy in the News. We're going to cover some of the things that are going on. With Matt mentioning that today is the anniversary of Scott Dureski's birth, I thought it would be a great time to look back these couple days, yesterday and today. There are a lot of really interesting anniversaries. So the first one is with the words let's go on 12th of April, 1961. Those were the words that Yuri Gagarin used to announce the start of his 108-minute voyage that would, for all time, be remembered as the start of a new era in the history of humanity. So yesterday, we celebrated the 60th anniversary of Yuri Gagarin's flight around the world, a single orbit that changed humanity forever. A test pilot's dream. Yesterday, we also celebrated the 40th anniversary of the first flight of the space shuttle, STS-1 Columbia, launched on the 12th of April, 1981. A test pilot's dream were the words of Robert Crippen, who was selected to accompany John Young on this very first flight of the space shuttle that would eventually lead to 135 flights of the space shuttle over a lifetime that lasted 30 years. Saw the deployment of the Hubble Space Telescope, the Chandra X-ray Observatory, 5 missions to service the Hubble Space Telescope. On this first mission, there were just 2 astronauts, John Young, one of the astronauts that has probably the most amazing career in the history of astronauts in the US Space Corps. He flew on Gemini twice, Apollo twice, and was the commander of the first space shuttle mission. Houston, we've had a problem. Today, we are celebrating, maybe not celebrating is the right word, the 51st anniversary of the Apollo 13 explosion. The explosion happened as Apollo 13 was about 2/3 of the way to the moon on the 13th of April, 1970 at 11:07:53 p.m. So if you happen to be up this evening at a little after 11 o'clock, think back to what was happening exactly 51 years ago. It's also a good night to watch Apollo 13, the movie, about what happened on that amazing mission and what turned out to be NASA's finest hour. And the last anniversary, I would argue possibly the most important of the 3, is today is the 136th anniversary of the dedication of McCormick Observatory. McCormick Observatory was dedicated on April the 13th in 1885. When it was finished, it was the largest telescope in the United States and the 2nd largest lens telescope anywhere in the world. And it's been in continuous use by the astronomy department now for 136 years. So those are just some of the anniversaries I wanted to get out of the way at the very beginning to think about what's been going on in the past. But now let's think about what's going on in the world right now. So the first story I have tonight is who ordered that? So for those of you that are familiar with those words, those were the words that were spoken by I. Rabi when he learned of the discovery of a new subatomic particle called the muon. No one expected that such a thing existed in the universe. In fact, the theories that they had of particles at the time didn't require this very bizarre, very heavy particle to exist. And so when he learned of its existence, he wanted to know who ordered that. That muon turns out to be really important in the news right now. So I have a bit of a trivia question for you. What's the difference between 0.001165920062 and 0.001165911810? Well, you can break out a calculator and see that the 2 numbers are very slightly different from one another in the last couple digits there. But if your answer was not the numerical difference, and you said, what's the difference between those 2 numbers? And that difference is the Nobel Prize in Physics, you could be right. So a recent experiment, and the results were announced just the other day, an experiment at the Fermi National Accelerator Laboratory in Batavia, Illinois, called the Muon G-2 experiment, is looking at these subatomic particles called muons. I'll talk more about them in a minute. And what they discovered is that the properties of the muon are not what are those predicted by the standard model of particle physics. And this difference might, and I'm going to emphasize the word might indicate that something odd is going on in the world of particle physics. Either there might be new particles and fields out there, or the standard model might need some correcting. So the experiment occurs at Fermilab, which is the largest particle accelerator in the United States. This particular experiment had been run previously at Brookhaven Lab in New York, and then it was moved here to Fermilab, and they've gathered more data here at Fermilab than all the other experiments in the world combined up until this point in trying to look at this anomaly with the muon. So what is the muon? These are all the fundamental particles in the universe. So astronomers and physicists, I'll give credit to physicists here, they call this the standard model of elementary particles. The standard model consists of all the particles that exist in the universe and all those particles that interact with these particles. That is, these are the interactions, the force carriers. The particles that exist in the universe consist of 6 quarks, the up, charm, top, down, strange, and bottom quarks. These are the things that make up matter. combinations of quarks make up the proton and the neutron that are in the nucleus of our atom. Associated with those and also making up matter are these subatomic particles called the electron, the muon, and the tau. And associated with them, these tiny little mysterious particles called neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino. The particle we're interested in today is called the muon. It was first discovered in 1936. It's identical to the electron in that it has a negative charge. It's just 207 times more massive than the electron. The particles over here on the right-hand side, these are the intermediaries. These are the things that carry forces in the universe. So the photon, for example, carries the electromagnetic force. And these bosons down here are involved in the weak nuclear force, another one of the four fundamental forces of the universe. So physicists have been measuring the properties of the muon. In particular, things like the electron and the muon act like little tiny magnets. And if you put a magnet in a strong magnetic field, it wobbles around. And that wobbling can be predicted by the standard model of elementary physics, the standard model of particle physics, to extraordinarily high precision. In the past, scientists have calculated exactly how the muon should behave in a strong magnetic field. And when they measured it at the Brookhaven National Laboratory, they saw that it was slightly different. Now, what's puzzling about this is that the standard model is extraordinarily good at predicting how these particles interact with one another. And when I say extraordinarily good, I mean it's not unusual for these results to be good to 10 or more decimal places. So the standard model accounts for all the particles in the universe and all the forces in the universe except for gravity. The standard model is sort of the gold standard of understanding what makes up matter in the universe. Well, the fact that muons weren't behaving was a really interesting result. So they followed it up with this latest G-2 experiment. And what they found with the latest data is that sure enough, the muon is not behaving as predicted. In fact, if you're interested, here are the scientific results. This is what the standard model predicts over here. And then this is the Brookhaven lab experiment result. This is the Fermilab result. This is the experimental average of those two. And you can see that it is very different than the standard model. So what does this mean? Well, it could mean one of two things. Either physicists need to go back with pen and paper and figure out what's wrong with the standard model, or it could mean that the muon is interacting with other particles and other fields that we don't know about. And what would be unusual about that is that the standard model right now is considered complete. That is, there's nothing that seems to be missing out of the standard model. We don't believe that the standard model predicts that there should be any new particles or any new forces in the universe. Now, that hasn't always been true. Up until 2012, the standard model predicted that there should be this boson called the Higgs boson, and we hadn't discovered it yet. But in 2012, the Higgs boson was discovered, and so now the standard model is complete. Inside the standard model, there's no room for additional particles or additional forces of nature. So if this result holds up, that the muon is not behaving as predicted by the standard model, it could indicate that there are new particles and new fields in the universe that are operating at the tiniest sizes inside of atoms, interacting with muons. And that, if it turns out to be true, would certainly be worthy of a Nobel Prize in physics. So keep your eyes open on that. Other big news in the world right now is the Ingenuity helicopter on Mars has had its first flight delayed for at least a week now. So you might be familiar with the fact that the Perseverance rover on Mars carried with it a small helicopter called Ingenuity. Ingenuity flew to Mars on the bottom of the rover. After the rover itself had checked itself out, it moved over to a safe flying area, dropped a pan off the bottom that had been covering Ingenuity. Ingenuity then proceeded to unfold itself from underneath the rover, deployed its 4 legs, and then the rover dropped it on the surface and drove off and left Ingenuity behind. In fact, this is a selfie that was just recorded by the rover the other day on its long robot arm that contains its scientific instruments. It has a camera, and it used its camera to photograph itself and Ingenuity sitting on the surface of Mars. Now, Ingenuity was supposed to have its first flight this past weekend. They tested it last week. They spun the rotors at about 50 revolutions per minute. Sounds like a lot, but that's small compared to the more than 2,000 revolutions per minute that they will spin those blades when Ingenuity goes to fly. On Friday, they were trying to spin the blades up to about 2,000 RPM when something happened inside the software. Fortunately, it was not a mechanical problem, but a software problem with Ingenuity. A little command timer, countdown timer went off when it wasn't supposed to go off. It shut the robot down. The robot radioed home for help. They've downloaded all the telemetry and they've identified a fix that they need to make to software. But that's going to require them to modify and reinstall the flight software on Ingenuity, and that's going to delay the first flight by at least a week to 10 days. So we're probably not looking to see the first flight of Ingenuity on Mars for another week or so. And the last thing I'll mention that's in the news is this is a really, really busy month on the International Space Station. This month, there are 2 launches and 2 landings in 4 separate spacecraft. On April 9th, just a few days ago, 3 new crew members launched up to the International Space Station, 2 Russian cosmonauts and a US astronaut. They launched on the Russian Soyuz vehicle. Interestingly, going back to how I began my presentation tonight, they followed some traditions in the Russian space program. Before leaving Moscow, they went to the Kremlin wall and they paid homage to Yuri Gagarin, where he is interred there. It is tradition that all cosmonauts that fly before they leave Star City, which is just outside Moscow, stop by the wall and they pay homage to the astronauts that are interred there that lost their lives in the Soviet space program. So these 3 cosmonauts laid flowers at the grave of Yuri Gagarin. Just before departing, they visited Yuri Gagarin's study at Star City. This is his office, exactly as it was on March the 27th, 1968, when Yuri Gagarin walked out of the office to go on what should have been a routine training flight in a jet aircraft that ended up crashing and killing Yuri Gagarin and his pilot instructor that day. So the office has been preserved as a historical monument to Yuri Gagarin, and every astronaut and cosmonaut that flies stops by the office and signs the guest book before flying to the Baikonur Cosmodrome and being launched into space. So these 3 astronauts launched up on April 9th to the International Space Station. They've docked with the space station and they will remain there for about 6 months. 3 more astronauts that are currently on, 2 cosmonauts and an astronaut that are currently on the space station will be returning home here in about 5 days on the 18th of April. They'll be taking their Soyuz spacecraft back to Earth. Just 4 days after that, NASA is launching the second Crew Dragon mission up to the International Space Station, carrying 4 astronauts, 2 US astronauts, a Japanese astronaut, and a European astronaut up to the International Space Station. And they'll be flying the Dragon spacecraft on the Falcon 9 rocket, launching from Cape Canaveral. Just 5 days after they arrive and arrive at the International Space Station, the 4 astronauts from the Crew Dragon 1 mission will return to Earth on their spacecraft and splash down just off the coast of California. At this very moment, there are 10 people living and working in space, and later this month, for a short period of time, we'll even have 11 people living and working on the International Space Station. So those are the big news articles. Thank you, Matt, and I'll turn it back over to you.
Awesome. Thank you so much, Ed. That's some great news to be hearing coming up in the next couple of weeks for astronomy. And this is not goodbye to Ed. We will be seeing Ed in another segment in about 30-40 minutes, where he'll be showing us about what's up in the night sky. And so say goodbye to Ed for now, but we will be seeing him as well in a bit. But for now, what we're going to be doing is we're going to be turning to our next talk of the night, and that is going to be by Dr. Rachel Beaton. And so Rachel Beaton, she got her PhD from UVA actually in 2014. So that was a year before I started. We never overlapped at UVA. But while there, she was very active in outreach, including helping start an outreach group called Dark Skies, Bright Kids, which I was a pretty active member in as well. In 2016, she was awarded the Trumpler Award for her UVA PhD thesis, which is awarded by the Astronomical Society of the Pacific for significant impacts by PhD students to astronomy. From UVA, she moved to Carnegie Observatory in California before heading to Princeton in 2017 with a Hubble Fellowship and a Carnegie Postdoc Fellowship to continue studying the structure of the universe. At Princeton, she's a part of what's called the ELVS survey, which extends our characterization of satellites of Milky Way-like galaxies to about 10 megaparsecs. So it's basically her thesis, but just tuned up to larger scales. Lately, her personal science has been using detailed characteristics of Milky Way and large Magellanic cloud stars to tighten distant measurements in the infrared for application to the Roman Space Telescope and the 30-meter class telescopes. And so pre-pandemic, she was back and forth between the US and Chile, but currently she has been, as she told me, revisiting her roots in Southern Virginia on the family farm. So go ahead and take it away, Rachel.
Hey, thank you. We'll share my screen. Okay. So the talk I'm going to give today is actually about the Hubble constant, which is what I've been working on lately. And I titled the talk "The Constant Hubble Wars" because, as I'm going to show you, the value of the Hubble constant, despite being incredibly important for cosmology, is incredibly difficult to measure. And we've actually measured it wrong more times than we've probably measured it right. So to begin anything, it's good to start at the beginning. And the Hubble constant was discovered by Edwin Hubble in a paper he published in 1929, where he published what is called the velocity-distance relation. So he measured the distances to galaxies, and he also measured their observed velocities. And he found that almost all of the galaxies were moving away from us. So not random motion where half would be coming towards us, half would be moving away. All of them are moving away. And the velocity with which they were moving away was proportional to their distance. So you fit this line and you get a constant of proportionality. So velocity is some value times distance. And we've called this value the Hubble constant. Today, in modern terms, the Hubble constant is the value of this Hubble parameter in the very local universe. And you can measure the Hubble constant at different points in the history of the universe, and we call it the Hubble parameter then. But it's really, so many things got named after Hubble after he made this and some of his other works. So it's really good to take a moment and actually acknowledge some of the foundational efforts that were required for him to make this discovery, for which many things have been named after him. So first of all, a lot of his work was aided by Milton Humason, who started as a mule driver at the telescope facility when it was being constructed, and then eventually measured the universe with Edwin Hubble. So to actually measure the velocity-distance relation, though, he had to measure distances. And the distances were measured using what's called the Cepheid period luminosity relationship, from which you can measure distances, which was discovered by Henrietta Swan Leavitt at the Harvard College Observatory. Henrietta Leavitt was a computer where she did computations. Eventually she was able to publish some of the work where she discovered the Cepheid period luminosity relation. You also had to be able to take spectrograms, so measure velocities, by taking data that spanned multiple nights. And the person who actually invented the technique and then took the first velocities of nebulae, of galaxies, was Vesto Slipher, who was working at Lowell Observatory. And actually about half the points on that plot were actually from Vesto Slipher as a private communication that was never cited in Hubble's paper. Lastly, I've described, and Hubble and I have described everything so far in terms of what he actually measured, velocity-distance relation. But to interpret it and to understand it physically, you needed a theoretical framework for how this fit into the universe, our understanding of the universe. And that was developed by Georges Lemaitre, who was working in Belgium. And so what is the velocity-distance relation? What does the Hubble constant really mean? To do that, you need this interpretation and implication phase, which was done by taking the equations of general relativity, doing some fun math that was also performed by Alexander Friedman, I put his picture here, and by Georges Lemaitre. And you eventually can come to the conclusion that if general relativity is right, the universe needs to be expanding. And you can actually derive the a prediction of the expansion rate of the universe just from those equations alone. And what it means if this velocity distance relation, which was predicted by Lemaitre, if we observe it and we see it, it changes a lot about how we think about the universe. The universe, if it's been expanding, it started a lot smaller. If it's expanding, it's not static. And the universe could be extremely big, and it could also be extremely old. So to ground ourselves in understanding this, we had to ask the question, how old and how big, which we get from the Hubble constant. So measuring the Hubble constant has been a history of controversy. And this is a plot of all the measured values of the Hubble constant over about 80 years. So year on the x-axis, Hubble constant on the y-axis. And the original values that were measured by Lemaitre, Hubble, and Humason are plotted here. They came out in the ballpark of about 500 kilometers per second per megaparsec. So kilometers per second is how we measure velocity. Megaparsec is a measure of distance. And we can see that by 2000, we had kind of changed the estimate of the Hubble constant by about a factor of 10. And so why would that be the case? So the really important measurement came by a colleague of Hubble's, Walter Baade at Carnegie Observatories, and his research was Henrietta Swope. And what they did was a little bit different. So when we talk about uncertainties, especially measuring parameters of the universe, there's two types of uncertainties. Random uncertainties, which talks about precision, which you gain by repeat measurements, and systematic uncertainties, which talks about the accuracy of your ability to measure something. And the only way to understand your accuracy is to have these independent measurements. So what happened in this case is that Walter Baade and Henrietta Swope found a systematic error that biased the value of the Hubble constant considerably. To do that, let's take a second and think about how we measure distances. So conceptually, this is fairly straightforward. We start with a candle, something that gives off light, and we study it up close and very up close. And we figure out how to standardize it. We figure out what its standard luminosity is, what its standard brightness is, and what parameters correlate with that brightness. And then, gotta wake up my dog for a sec. And then if we take that candle that we've characterized very well, that we've now standardized, and we push it very far away, we can use the relationship between the brightness when it's far away and the brightness when it's close to derive a distance. And from the distance, we can get a Hubble constant. So in this very simple example, it all makes a lot of sense. But we did something with an idealized candle, and where we can take that ideal candle and we can put it really far away. But if we actually look at actual candles, so these are candles that I had around my house, and you'll note that I have LED candles, I have candles that are pillars, I have candles that are, the long skinny ones, lots of different candles, even candles powered by different mechanisms. And when we put real candles that have lots of nuance, the wonderful nuance of the universe, and we push them far away up here in the corner, some of that nuance about which candle is which gets lost when they're very far away. So the analogy I want to make is that it's very hard to tell the LED and the fire candles apart when they're pushed quite far away. And what that means for Walter Baade and Henrietta Swope is that they determined type variables that Humason had been using weren't a single class of objects. They actually formed two classes of objects. So the type 1 and the type 2 Cepheids, meaning one is from an older population of stars and one is the young population of stars that Henrietta Leavitt had studied and characterized. And once they threw out those type 2 Cepheids, the universe changed in size by a factor of 2 overnight. So after bigger telescopes came online, the measurements sort of settled down and bounced between a range of 50 kilometers per second and 100 kilometers per second. And this was known as the factor of 2 controversy. And it really was a battle between two prominent physicists of the time, everybody else. So Gerard de Vaucouleurs at the University of Texas, Austin, working at McDonald Observatory, and Alan Sandage and his allies working at the Carnegie Observatories, both at Mount Wilson and at Palomar. And I've color-coded their measurements. So Gerard de Vaucouleurs is in green and constantly bounced with that random motion that we'd expect, constantly bounced around 100. Meanwhile, Alan and his collaborators constantly bounced around 50. But there's a systematic difference of a factor of 2. And this was not a pleasant argument. This was a very vitriolic argument. It was an argument that you could get in the way of and be one of these other blue dots in publishing, and your career and your life would be very difficult. So eventually the community was looking at this and came together and said, we need to solve this problem. But what's the origin of the argument? So I talked very simply about a single standard candle, but it turns out we don't actually have a single standard candle that can get us all the way out to the distances that we need to probe. So what was constructed in the mid-20th century was what's called a ladder, where you step out one rung, you tie to a different distance technique, and you step out and you step out and you step out. So first of all, that builds a lot of uncertainty as you go through. Those uncertainties propagate forward, but it also means that you make a lot of techniques and you make a lot of choices. And those individual tests and choices have communicated, you use different data. So it was kind of the opposite of open science, and it was very hard to understand how these two guys, sometimes using the same data, or similar data, we get such different answers. So the community came together and said, we're putting up, in 1990, we're putting up this beautiful Hubble Space Telescope, one of the major accomplishments of humankind. It would really be not good if we couldn't solve this problem with the Hubble constant. And so these teams were put together, and the Hubble Space Telescope Key Project was born. And it took about a decade to go from getting the telescope up there, fixing its mirrors, getting everything done, to when they published a value of the Hubble constant of 72 kilometers per second per megaparsec with about a 10% uncertainty. And I like to classify this project as hard and careful work. They actually looked at all the different distance indicators that people were using. They figured out how to put them all together into a consistent framework. They worked together to develop tools and techniques, some of which we still use today, and we probably don't realize that they came from the Key project. But at the same time that this work was published in 2001, there had been a discovery in 1998 called the Discovery Accelerating Universe. So we've talked about how the universe is expanding, and we talked about this Hubble parameter, but the Hubble parameter is actually changing over time, and the universe is accelerating. And we didn't know, so there were hints that that something was going on in cosmology, but we didn't know that we didn't know this when we were trying to reconcile these different measurements. And it turns out that Alan Sandage was actually using the age of the universe as measured in star clusters as a prior on all of his other measurements. And it turns out, and these star clusters were much older than a high Hubble constant could give you. But if the universe is expanding and the Hubble constant started smaller and now has gotten larger, sorry, the universe is accelerating and the Hubble constant used to be smaller, it's now larger, you can have extremely old star clusters and a high value of the Hubble constant. So to solve this problem and this controversy, we had to have a combination of really hard, careful work and the discovery of something that we didn't know we needed to be looking for. Now, while the Hubble constant factor 2 controversy was being argued and solved, there was a really important discovery by Penzias and Wilson at Bell Labs. And Penzias and Wilson discovered the cosmic microwave background. And the cosmic microwave background is literally seeing what was left over after the Big Bang, right before the universe changed drastically. And what that gave us was a way to actually measure. So first of all, this was predicted. And so finding it was good, but it gave us a way to measure the very early universe. And now we have, and when we're local, we measure the current universe. So we now have bracketing information about the evolution of the universe as it corresponds to its expansion history. So I've plotted here. Whenever you see these little symbols here, that means Nobel Prize winning discovery. So Penzias and Wilson were awarded a Nobel Prize, and the team that ran the COBE satellite was awarded the Nobel Prize. And members of the teams that discovered the accelerating universe were also awarded a Nobel Prize. And these studies of the cosmic microwave background have gotten better and better over time, the 1990s version, the 2000s version, and now we work with the Planck satellite in 2010. So both of these techniques give us a way to actually understand the evolution of the universe, and they give us a measure of the Hubble constant. So over the past decade, so from 2000 to 2010, the blue measurements, which were coming from the distance ladder, the traditional way to measure the Hubble constant, where we measure it directly, and those measurements coming from the cosmic microwave background, which are in red and indicated by their satellites, agreed. And this was during this kind of classic era of cosmology when all these different ways of knowing about the universe all seemed to agree. And we thought we just understood it really well. But soon after, Adam Rees, who's part of the dark energy discovery team, had simplified the ladder so that it's just a geometric anchor. We use the Cepheids, and then we use our friends, the supernovae. The error bars started getting smaller on our local measurement. And as the error bars started getting smaller, the error bars on the cosmic microwave background measurements got smaller. We now disagree. And these tensions are actually large. We call this the Hubble constant tension. And it's a big issue in cosmology today, because in the past, it's led us to find something like the dark energy, the accelerating universe. And that could be what we're finding here. And understanding that requires understanding a little bit about how you measure the Hubble constant from the cosmic background. What you do, take this what's called a power spectrum. It just means where the energy is at a function of angular size. So on small sizes to big sizes. And what you do actually measure the Hubble constant is you measure a set of parameters for the standard model, which you can measure extremely precisely. And then you compute the Hubble constant, so the local value. So what's important to understand is that by fitting a model, these measurements can never tell us if we're missing something from the model. It can only tell us how well we can measure things in the model. And so that means that if our very local measurement that's measuring exactly the Hubble constant versus what's computed from a model fit cosmic microwave background, if those are disagreeing, it's either telling us something's missing from the model or something's fundamentally wrong with how we're measuring the Hubble constant locally. So in 2016, I was on a team that proposed a test of the Cepheid distance scale. And the reason we wanted to test the Cepheid distance scale is that it's actually really, really complicated. So you ultimately measure a distance by fitting something called the Leavitt law to a distribution of stars in period and luminosity. But these values aren't just values that you measure once. You actually have to fit them by measuring a light curve over 60 to 120 days. So just monitoring that star and figuring out its mean brightness. Then you have to think really carefully about how you're making those measurements, because Cepheids sit inside of some of the densest parts of their host galaxies. So you really have to worry about their local environment contaminated systematically when you're making these measurements. Lastly, while our mathematics actually really well describe what happens in the core of a star, what happens in the atmosphere is a bit different. And the atmosphere of a star has atoms and molecules that make chemistry, and those atoms and molecules absorb light, which change the brightness of the star. So these are all things that we have to worry about when we use Cepheids. So my team, or the team I was on, proposed that we use something a lot simpler. And we're going to call this the tip of the red giant branch. It's a statistical technique. I don't look at individual stars. I look for the truncation of a sequence of stars. I'm using old stellar populations, so they're not young. They were born a very long time ago, and when the universe was very similar to itself, and they're very similar to the ones in our own backyard. And the metallicity and the chemistry of these stars just hadn't had enough time to get weird, like it could get weird in the Cepheids, which are young stars. The other advantage is that we don't have to work in the spiral arms where these galaxies are very complicated. We actually work way out in their halos. And their halos, so this is an actual image inside the halo of a galaxy. You wouldn't even know you're looking in a galaxy. You're literally looking right through it. But buried in here are lots and lots of little stars that we measure to make this distance. And so we've literally eliminated a ton of the systematics that could be impacting the Cepheids. So here's an example when I go in and I measure the colors of those stars. This is the red giant branch, and there's its truncation. And it's really just a mathematical problem to figure out how we detect that and measure it and get our uncertainties. And so we did this for a lot of galaxies that host supernova type 1a. I spent a ton of time worrying about systematics. I worried about a lot of random precision related things too, and I worried quite a bit. And my mentor, Wendy Friedman, who had led the HST Key project, published our results in 2019 and 2020. where we actually measure a value of the Hubble constant here. This is our result that is actually dead in the middle between the cosmic microwave background and the Cepheids. So we had hoped their value would either agree with the Cepheids, which says there's nothing wrong with the local distance scale. It must mean missing from the standard model, or it would align perfectly with the cosmic microwave background, saying we've just made mistakes with these Cepheids and now we go and understand them. Instead, we came out in the middle, which is the least exciting place to be, because I have no idea what it means, in the sense that it could mean that this tension is real and there's new physics. It could mean that we have more uncertainties to track down and more work to do in terms of measuring the Hubble constant in the local field. And learning from the history of measuring the Hubble constant, we've made a lot of mistakes in the past. And the other thing is that we don't have a theory beyond the standard model that helps us interpret what this difference might be. So people right now are writing lots and lots of theories as a framework to understand the tension, but it's much like when you look at the Mona Lisa. Everyone agrees that this is a magnificent painting, but we all see different things in terms of what the Mona Lisa may or may not be telling us or communicating to us. So it's clear that the universe is trying to tell us something with the discrepancy between these measurements. And I trust and I have faith that we'll understand it eventually. Okay.
Is that it? Is that it, Rachel?
Yeah, that's
okay,
it.
sorry, I wasn't sure. Yeah, thank you so much. That was awesome. So I think we do have time for one or two questions, and you guys are welcome to Q&A in the chat if you have any questions for Rachel. But I had a question for you in regards to, of course, people want some sort of resolution to this constant Hubble war tension. Do you think that the James Webb Space Telescope will provide any help in that regards? And if not, what sort of telescopes going forward might help us out in sort of resolving this tension?
Yeah, so the James Webb Telescope is going to take our aperture in space from about 2.5 meters in diameter to 6.5 meters in diameter, which means we're going to have a much larger collecting area, and we can see things that are much, much fainter and hopefully further away. But the gains are a little bit not matched, because we find Cepheids in the optical, where their variation is the largest. And it also means that we can type different types of stars that have Cepheid-like variations. When we move into the infrared, they actually all look the same. So we lose that ability to tell between those type 1s and those type 2s, and we have to guess a little harder. The other thing is, although we're getting much better spatial resolution with the James Webb in the infrared, much better than HST, well, much better, it's not that much better. So we'll be able to see much fainter things, but we won't actually be able to resolve the stars inside of them much further than we can with the HST.
Right.
So it's kind of a mixed bag for Cepheids. For our tip stars, provided we can calibrate it, and there's a lot of work on my desk trying to do this, we can possibly go extremely far and measure distances. We might be able to skip the supernova altogether, which would be great, although I love supernovae. But the other things to be excited for are the 30-meter class telescopes on the ground, which will have much better resolution than even the James Webb, and much larger collecting area. And they're going to let us do distances at extremely large distances, way out into the Hubble flow in about an hour. So what takes me 16 to 20 hours on HST now would take like 20 minutes on a 30-meter telescope.
Oh, wow.
So yeah, it is a huge jump.
Yeah.
The other place that'll be fun is the Raman Space Telescope, which will have a large field of view, which for the tip of the red giant branch measurements like I use means we'll have lots of statistics to play with in the outer halos, because the James Webb has the tiny, tiny, tiny field of view.
Right.
And one thing I worry about a lot is that you're just not going to get the sample that you need in that tiny, tiny field of view.
Okay, cool. Makes sense. All right, nice. So then I think we have time for maybe one more final question. And that's this. So over basically since the Big Bang to present day, some of the things that's talked about in cosmology, right, is this evolution of the Hubble constant. It's not truly a constant, right? So I was curious if you can talk a bit about how you can sort of observe or figure out what the Hubble constant, how it's changed over time, and how this could impact the the present, the sort of deviation of the two different measurements, and if that has any sort of implication towards that discussion at all.
Yeah. So we have two ways at getting to sort of the middle ages of the universe. One way is to look at supernovae that are further and further away. So I think the furthest known supernova is at a redshift of 2, which is about halfway through the age of the universe. With the space telescopes, you'll definitely be able to find more of those supernovae at extremely large distances and ages in the universe. The thing we don't know is we're not really sure if there's going to be evolution in what supernova look like nearby versus what they look like at early times or halfway through the age of the universe. That's always this big open question because we don't know exactly how supernova happen. We know it's a white dwarf going over what's called its Chandrasekhar mask and it explodes and it's very exciting. But we don't know if that happens because two white dwarfs are circling each other in a binary configuration. So another reason why binaries are very useful, or if it's a single white dwarf and a big puffy red giant star like I use for distances, and something happens between those two. And it could be that it's both of them. It's probably both of them, and the proportions of those are going to change over time. So that's one thing we worry about. The other way to look at the evolution of the Hubble parameter is to look at the clustering of galaxies on large scales. So it turns out the universe likes to cluster on a specific scale known as its acoustic frequency. It's basically a characteristic frequency or characteristic scale that you get out of the cosmic microwave background. And if you evolve that forward, and this got a Nobel Prize, by the way, Jim Peebles working all this out, got a Nobel Prize last year, as well as many other things that he worked out, is that those matter fluctuations are going to show up in where galaxies form. And over time, those expand. So there's a characteristic length scale called the sound horizon scale that you can observe throughout the history of the universe. And that gives you the evolution of the Hubble parameter over time. And you can tie these two types of measurements together in this middle zone. And it turns out if you do that, even today, if you do that, just the other end, whether you calibrate locally or you calibrate further away, the other end just is free. So this difference we're seeing between the cosmic microwave background and the local measurements is very real. We don't meet in the middle in any sort of good way. But I have some colleagues in Australia who are trying something really incredibly cool, which is to look for this clustering scale in the extremely nearby universe. And it has to use some of the most incredible technology because they need to measure the positions of many galaxies over huge areas on the sky. And so they created these little things called starbugs that march across a telescope's field of view so that they can reconfigure the telescope to measure as many redshifts as they need. Oh, wow. So I think that's a super interesting result because you could use the same, well, when it comes, it's just starting now or it's been delayed by the pandemic, but then you'd be able to use basically the same technique from the nearby universe all the way to the early times.
Oh, cool.
And if we don't find agreement there, it might mean because that characteristic scale is determined directly from general relativity and the standard model. And if that starts to look hairy, then there's a problem with general relativity and the standard model. Now, we just saw a small issue with the standard model, the muon discrepancy, right. And where that evolves will be really interesting because changing the neutrinos that interact with muons is one way to solve the Hubble constant tension. There's like another 10,000 other theoretical ways to do it because it's really fun to come up with ways to solve the Hubble tension.
Yeah. Sounds like it's certainly another Nobel Prize waiting to happen for sure when that is resolved. So lots of Nobel Prizes in cosmology, it turns out, which is nice.
Yeah.
But yeah, anyway, so unfortunately, that's all the time we have. We are going to be moving on to the next segment. Thank you so much, Rachel. I'm going to take some of that back to my cosmology class to talk a lot about the Hubble constant with them for sure. So thank you. And so what are we going to be doing next? We're going to be doing some astronomy trivia. And so that requires me to be sharing my screen. And so hopefully in the chat, Catherine can share with everybody the link to our trivia for today. And so this trivia was designed by Jacob White. He's another organizer at in Astronomy on Tap Charlottesville, and he made a nice fun spring themed trivia for us today. And so if you want, as usual, so you can get the trivia at this link right here. And of course, if you are willing to include a link to your email, I might reach out to some of the winners of the trivia to get some prizes like the various coasters, posters, and some books that we have that we can mail to you wherever you are, probably just in the United States. But if somebody wins outside, maybe I'll be able to figure out a way to get it to you guys there as well. So let's go ahead and dive into the trivia question. So question number 1, hang up that winter coat and dust off your swimsuit because spring is upon us. In the Northern Hemisphere, which of the following happens at the start of spring? Is it that the days get longer, the days start getting shorter, the days start getting longer at a faster rate, the days get longer at a slower rate, or day becomes night and night becomes day? So I'm gonna give everyone a couple of seconds to go ahead and click on the Google Doc for that if you want to, but we're gonna have to get going because we are a little bit behind on schedule. And so I'm gonna be moving through this a little bit quick, I think. Question number 2, seasons on the Earth do not depend on the Earth-Sun distance, but how big is the distance between the Earth's closest and furthest approaches to the Sun? Is it 5 kilometers, 500 kilometers, 5,000 kilometers, 5 million kilometers, or 5 light years? And so it turns out that the Earth does not revolve in a perfect circle around the Sun, and there is some slight deviation between its closest and furthest approach. All right, trivia question number 3, springs. Speaking of springs, springs can help you jump higher, or you could just go to Pluto. If you can vertically jump about 1.5 feet on Earth, how high could you jump from Pluto's surface? And would you be able to jump 5 feet, 10 feet, 15 feet, 20 feet, or 25 feet? And this is all dependent on whatever the surface gravity is of Pluto. The surface gravities of all the different planets is dependent on their mass and their radius. And so it turns out that Pluto's is smaller because Pluto is a lot less massive and smaller as well.
Hey, Matt.
Yep.
A couple of people have reported in the chat, and I can confirm from trying it myself that it appears the link we have been sent people is the link to edit the survey and not to answer the questions.
Oh, no way, really? Well, then maybe people could just fill it out on their own right now, and I can get a piece of paper, write down what your answers are, and I will send a better link to people in the chat after I figure that out, because I can't figure that out in the moment while I'm doing it. So I will definitely send that to everyone afterwards. Sorry about that. Make sure not to edit the answers or look at any of the answers. Let's move to question number 4 then. If the seasons on Pluto were at the same fraction of its orbital period as on the Earth, meaning that 25% of its year is spent per season, how long would spring last on Pluto? And this was given as a hint in our Facebook hints today. Would spring last 5 days, 7 weeks, 13 months, 62 years, or would there be never-ending spring break? Let's see if Brett sent the proper link there. I appreciate it, Brett. I thought I had everything figured out today too. I had so much time, so much free time. Oh well, it happens. Question number 5, spoiler alert, Mars has seasons. About how long does its spring last in its northern hemisphere? Is it less than a month? Is it 7 months, 12 months, 24 months, or 36 months? And at this point, just want to take a break to remind people that we are trying to collect donations for the Charlottesville Area Community Fund. That link is located here as well. If you're able to donate anything, it would certainly help alleviate some of the effects of the COVID-19 pandemic on the Charlottesville community. And so we'd certainly appreciate what you're able to give. All right, question number 6. Staying with Mars, which of the following events happen every Martian year during the Martian Spring? Does the CO2 or the carbon dioxide sublimate from its poles? Do the ice caps melt and the planet floods? Do the dust storms on its surface stop? Do Martian flowers bloom? That'd be nice. Or does Matt Damon finally come home? I'll give you a hint on this one. Matt Damon never truly comes home in any of these astronomy movies, so it's probably not E. All right, question number 7. Just like the moon is tidally locked to the Earth, a planet could be tidally locked to its star? How would we experience spring if the Earth was tidally locked to the sun? Would it be the same? Would the seasons be shorter? Would the seasons be longer? Would the sun explode? Or would we not have seasons? All right, question number 8. Easter is an excellent holiday. In the Gregorian calendar, which is the one we currently use, how is the date of Easter actually determined? Is it the first Sunday after the first full moon after the vernal equinox? Is it the first Sunday after the vernal equinox? Is it the 12th Sunday after the start of the new year? Is it the Sunday after the 3rd lunar cycle? Or is it whenever the Easter Bunny finally sends a save the date notification? All right, question number 9. Speaking of spring, what about spring tides? These don't have anything to do with the season, but what are they? Is it the first low tide of the vernal equinox? Is it the first high tide after a new or full moon? Is it when there is a high tide and the moon is visible? Is it high tide when the moon is aligned with the center of our Milky Way galaxy? Or is it when a bunch of old slinkies wash up on the beach? And then question number 9, this is coming directly from Jacob himself as he was writing. He says, I can't think of any more spring-themed questions. So here's one about astronauts. Which astronaut has spent the most consecutive time in space, as in during a single mission? Is it Mark Watney, Scott Kelly, Valery Polyakov? Sorry, I should have looked at the names a little bit beforehand. Is it Jeff Williams or is it Neil Armstrong? All right, and so that is our trivia for today. Make sure to fill out that trivia form that hopefully that's working for you guys, the one that Brett has sent. And you're able to submit that up until the end of the final talk tonight. But for now, what we're going to be doing is we're going to be turning back towards Ed, and Ed's going to be telling us about what's up in the night sky. And so Ed, you can go ahead and bring your video back up, start sharing your screen, and let us know some of the cool things that we can see in the night sky coming up in the next month or so. So Ed, what's up?
Perfect, Matt. Can you let me share my video? It says the host has stopped.
Sorry, let us give us a second to figure that out.
There we go. I think we're.
You good now?
Yep.
Okay, cool, nice. It wouldn't be an Astronomy on Tap event without just a couple of technical difficulties, so that's okay.
Well, I thought with everybody getting outside now that spring is here and it's a beautiful time of the year to get outside and look at the sky, I thought we'd talk a little bit about what is up in the night sky right now. So if you don't have access to a good star map, there are lots of good apps that you can download for your phone. You can get star maps on the computer, but sometimes a good old-fashioned paper star map is the best way to go. And my favorite one comes from skymaps.com. You can go to skymaps.com, you can download a free map there, you can print it out, take it outside with you, and I think sometimes paper just works best of all. So these are the stars that are up in April of 2021. This is what the sky looks like now about 10 o'clock in the evening, late in the month of April. This is what the sky will look like around 9 o'clock in the evening. And since most people said at the beginning tonight that their favorite thing to look at in the sky is planets, I thought I would tell you about all the planets that are visible tonight. Except that looking at the star chart, there's only one and is not very good. So if you look along the ecliptic here, which is the path of the sun through the sky, the planets will always be clustered along the ecliptic, along that path. It passes, of course, through the famous zodiacal constellations like Gemini, Cancer, Leo, Virgo, and Libra, the ones that you recognize. But only one planet's visible right now, and that's Mars. And Mars is, at best, I would call it moderately bright right now. And that's because Mars is on the far side of the sun from us. So it looks like just a moderately bright star, not terribly bright, not nearly as obvious as it was about 6 months ago when it was really quite bright. And more importantly, if you were to look at it through a telescope, because Mars is on the far side of the sun from us, it looks like a little tiny dot and you can see hardly any features. And other than Mars, I'm afraid there's nothing else visible in the evening sky. If you'd like to see Jupiter and Saturn, you have to get up right before sunrise. And then the other planets are all lost right now in the glare of the sun. Well, with no bright planets to see, you'll just have to turn your attention to the constellations. And springtime is the best time of the year to see what I consider, for those of us in the Northern Hemisphere, to be the best and the easiest to find of all the constellations. And that, of course, is Ursa Major, or the Big Dipper up there in the sky. The Big Dipper right now, about 10 o'clock in the evening, is high overhead. It's impossible to miss. And it's a great one to start with because we're going to use it tonight to find a bunch of other constellations. So the first thing you want to work on is finding the Big Dipper. Now, it gets its name. 4 stars form the bowl of the Dipper, and 3 stars form the handle of the Dipper. And it looks like a giant spoon up there in the sky. That's where it gets its name, the Dipper, the bowl of the spoon and the handle of the spoon. That said, not everybody calls it a dipper. In Great Britain, it was known as the plow. These 3 stars form the blade of the plow, the handle of the plow that you harness the team of horses to. In much of Europe, it's known as the wain or the wagon. The 4 stars of the bowl make up the wheels of the wagon, and the 3 stars make up horses pulling the wagon through the sky. Now, all of these, the plow, the wagon, and the dipper, are actually asterisms. They're not a constellation. An asterism is a geometric shape of stars in the sky. They can all be in one constellation, or it can be stars from different constellations that makes an easily recognizable figure or geometric shape in the sky. The constellation itself is actually Ursa Major, the Big Bear. And a lot of people have trouble seeing the bear up there in the sky. And first of all, that's not too surprising to me because the stars don't know anything about bears, right? The stars didn't organize themselves in the shape of a bear. The stars are just randomly scattered in the sky. Our ancient ancestors did the best that they could with what they were given in trying to identify things in the sky, because by identifying them and naming them, that's the first step into understanding what's going on in the sky. If you're going to teach the stars to your children, you need to have recognizable patterns and you need to give names to them. And they did the best that they could with what they had. So here is Ursa Major, the Big Bear. I always think of this as the nose of the bear, the eye of the bear, the front leg coming down to 2 toes on the front paw, the body of the bear, 1 back leg on the bear, another back leg on the bear, and then, of course, the big long tail on the bear up there in the sky. So that is our stick figure drawing of a bear up there in the sky. Now, in order to get to some of the springtime constellations, I'm not going to tell you the stories about Ursa Major. They're some of the most famous constellation stories, and they come up over and over again. So I want to focus on the spring constellations. So I'm going to skip past it, except for the fact that Ursa Major, once you have found the bear up there in the sky, it's a great object to use to find other things in the sky. For example, many people know that the easiest way, I would argue the best way, to find the North Star Polaris is to use the N stars in the bowl of the Dipper. The 2 N stars in the bowl of the Dipper, if you follow them, they point right at the North Star Polaris. That is, you find the bowl of the Dipper, find these 2 N stars, and you just draw a line between them and keep going, and you will eventually get to the North Star Polaris. Now, Polaris is just a moderately bright star in the sky. It is nowhere close to the brightest star in the sky. And that's a common misconception I hear amongst people, that they think Polaris is really bright, and it's not. It's just a moderately bright star. And that means that the safest and best way to find it is to use these 2 pointer stars. Of course, Polaris sits right above the North Pole of the Earth. Not exactly above, but pretty close to almost straight above the North Pole. And so as the Earth turns from west to east, all the stars in the sky turn east to west around the North Celestial Pole, which is marked by moderately bright Polaris there. Well, let's use that Dipper then to find other springtime constellations. Because once you've identified the Dipper, it's distinctive enough that you should be able to go out on almost any night of the year and be able to find it again. And once you've found it the first time, now let's use it to find other constellations. And the first thing we're going to do is we're going to take these 2 back stars in the bowl right here. And instead of following them up, we're going to follow them down towards the south. And as we follow those 2 stars down to the south, we come to the constellation of Leo the Lion. And Leo has a very distinctive backwards question mark associated with it. These are the stars of Leo the Lion. And we call this backwards question mark the sickle of Leo the Lion, or sometimes just the backwards question mark. And they make up the head and the mane of Leo the Lion, leading down to this bright star Regulus, which is the heart of the lion. These three stars back here make up the back leg of the lion, and that's the tail of the lion right there. In fact, if we draw all the stars in, that is Leo up there in the sky. And I think, remarkably, it looks like a stick figure drawing of a lion. I think our ancient ancestors did a pretty good job with Leo the lion. Now, you might wonder, why is there a lion up there in the sky? And this lion represents the first labor of Hercules. You'll remember that Hercules was given a series of labors, and one of the labors was to slay the Nemean Lion. Now, this Nemean Lion had been terrorizing the countryside in the country of Nemea, and he was given a task of killing the lion and bringing the skin back to Eurystheus. The lion was the son of the monster Typhon, and he was suckled by Selene, the goddess of the moon. So the lion had supernatural powers. Now, Hercules went to Nemea, and he searched through the forest of Nemea looking for the lion. And he brought with him a sword. He had with him a bow and arrows that he had made. He even had with him a club that he had made from an olive tree that he had pulled out of the ground with his own bare hands. While he was in the woods, the lion attacked Hercules. And Hercules quickly discovered that his sharp weapons, his bow and arrows, his sword, had no effect on the lion. He eventually chased the lion to a cave, trapped the lion in a cave, and was able to strangle the lion with his bare hands. Hercules found that the skin was so tough that he couldn't cut it off with his sword or with his bows and arrows. And so eventually he was forced to use one of the lion's own claws to remove the skin. Hercules later on used this impenetrable skin as a shield. And when you see Hercules depicted in mythology, you often see him with a raised left arm, and draped over that left arm is the lion skin, with Hercules using it as a shield. So that's how we have a lion up there in the sky, and that is Leo the lion, the Nemean lion. All right. Now, we're going to go back to the Big Dipper here for a second, and we're going to follow the arc of the handle right here. And the arc of the handle comes down to the really bright star Arcturus. Arcturus has a distinctly yellowish orange color to it, and it is a part of the constellation Boötes. And Boötes is the plowman or the herdsman. He walks behind the plow or the bear up there in the sky. The name Arcturus means bear follower or bear watcher, and Arcturus watches the bear. And the name Arcturus comes from the Greek for bear, and that is where we get our word Arctic from. It comes from the bear up in the northern sky. And so Boötes is simply a stick figure drawing of a man. He's got a head and two shoulders, a waist, and his two legs coming down on either side. So that is Boötes, the herdsman or the plowman, or sometimes just simply known as the bear watcher up there in the sky. The next constellation, if you follow the arc of the handle down to Arcturus, remember arc to Arcturus, you can then drive a spike down to Spica, which is in the constellation of Virgo down here. Now, Virgo is a really big constellation, but it's mostly made of faint stars. And the best way to find it is arc to Arcturus and spike down to Spica, and you'll come to Virgo. Virgo represents the goddess Ceres, the goddess, or represents the daughter of Ceres, the goddess of agriculture up there in the sky. So, the story around Virgo is Ceres' daughter Proserpina was a very beautiful young woman, and she was out on the beach one day collecting flowers when Venus happened to come by with her son Cupid. Now, Venus was upset that Pluto had not yet found himself a wife. He had not found himself the love of his life. So she told Cupid to shoot Pluto with one of his arrows. As soon as Pluto shot Cupid, he would fall in love with the first person he would see, and he happened to see Ceres there. And so as he saw Ceres, he fell in love with her, and he took her down to the underworld to make her his wife. Now, unfortunately, Ceres lost her daughter. She looked all over to find her daughter and she couldn't find beautiful Proserpina. She went to the bear in the sky and asked the bear if he knew where her daughter was. And the bear did not know where her daughter was, said, check with the sun. The abduction happened in the day. Maybe the sun knows. The sun told Ceres that he had seen Pluto take Proserpina to the underworld. And so Proserpina went to the god Jupiter and asked to get her daughter back. Jupiter agreed that Proserpina could come back on the one condition that she hadn't eaten anything when she was in the underworld. But unfortunately, she had. She had eaten some pomegranate seeds. Ceres was so sad that she stopped letting the crops grow. And Jupiter couldn't allow that to continue, so he came up with a deal. And the deal was that every spring, Proserpina would leave her husband in the underworld and come join her mother Ceres, the goddess of the agriculture in the sky. When that happens, Ceres becomes happy, the crops start to grow, and they will grow for the next 6 months until when the fall arrives, under this deal that Jupiter cut, Proserpina is forced to return to the underworld, where she'll spend the next 6 months with her husband, Hades, or Pluto, the god of the underworld. And in those 6 months, Ceres is sad, missing her daughter, and the crops don't grow. So this is the perfect time of the year to go up and find Virgo in the springtime. So those are some of the springtime constellations that are up there. I'm going to go ahead and leave it there because I'm out of time, but use the Big Dipper to find the North Star Polaris, use it to find Leo, and use it to find Virgo, some of the most prominent of the springtime constellations. Thanks, Matt.
Awesome, Ed. Thank you so much. Always great to hear a lot of those fun constellation stories for sure. And I actually didn't even realize that Mars was up tonight, so I'll definitely make sure to check that out. I still do enjoy looking at Mars and some of the other planets. For sure. But unfortunately, we're running a little bit short on time, which means we got to head up to our final speaker of the night, and that is going to be Wes Rile. And so Wes Rile comes to us from Thomas More University, where he's a professor of physics and astronomy, and he's been there since 2008. And Thomas More, for those of you that don't know, it's a small liberal arts college near Cincinnati, Ohio. And we were able to make this connection with Wes through Whitney Richardson, who some of you guys might know through the Astronomy on Tap Charlottesville community, because they went to school together at Western Kentucky University. So Wes is additionally, in addition to being a professor of physics and astronomy, he's the campus observatory director, which we might be linking the link to the Facebook link to that observatory in the chat. And he got his PhD from Georgia State University, where he focused on understanding supermassive black holes in distant galaxies. But more recently, his research interest has been on binary star systems, which is the focus of his talk today. So go ahead and take it away, Wes.
All right, thank you. And thanks for having me. So we're going to talk a little bit about binary stars and the role binaries play in a lot of other important astrophysics. It's kind of nice that Rachel was talking about cosmology ideas because there's going to be some tie-in there. And also nice that Ed was talking about the Big Dipper because we're going to mention that here in just a second as well. First off, keep in mind that it's actually really hard to measure the basic properties of stars. And those basic properties are things like mass, radius, the size of the star, and the temperature of the star, the surface temperature of the star. I've also put distance in there as a very hard thing to measure for stars, even though it's not necessarily a property of the star, but a property of the star's location. The thing to keep in mind is that there is a wide range in the properties of stars that we've observed out there. And so there's a wide range in mass, a wide range in size, and a wide range in temperature. There are stars that are significantly larger than the sun, and some of those are much hotter, some of those are much cooler than the sun. There are also stars that are significantly smaller, and those can be, again, hotter or cooler than our sun. Our sun is, in some ways, an average star in terms of temperature and mass and radius of all the stars that are out there. Now, the reason that we're interested in the properties of stars and the reason that binaries can play such an important role in astronomy is that they're really vital to understanding a lot of the other, what I call sexy topics in astronomy. Cosmology is definitely one of the sexy topics in astronomy. It's one of the ones that has a big draw for new PhDs. And definitely is a big area of research right now, another one being extrasolar planets. The reason that the properties of stars can play a big role in those kind of ideas is that the mass of a star in particular is kind of the single most important parameter for how a star is going to live out its life. You can have really large massive stars go through nasty eruptive events towards the end of their lives and eventually go supernova. And those supernova explosions can be very important as distance indicators, as Rachel mentioned. Very interesting things like black holes or neutron stars and black hole binaries or neutron star mergers that produce gravitational waves. All those objects, neutron stars and black holes, began as stars, and knowing the properties of those stars gives us better information about how they transformed into these more exotic objects. Obviously, for extrasolar planets, you're very interested in the properties of the star that that planet is in orbit around, because that's going to control the habitability of that planet. And then lastly, even at bigger scales, things like galactic scales or even cosmological scales, when you're talking about a galaxy, really the majority of the light that's coming from that galaxy is coming from the stars within it. And so knowing a little bit more about those stars is important for knowing the overall properties of the galaxy. Now, I'm going to throw this slide up here, and just to panic some folks, we can create theoretical models of stars. And as Rachel mentioned, we're very good at modeling the deep interior of stars and the cores of stars. And we can actually use these models. If we have a mass of a star, we can use that to predict its radius and its temperature if it's in a nice stable state. And it's some really gory math and physics that goes into that, differential equations that you can solve. But the funny thing is that if you go through and solve these equations and actually produce what you think a star should look like, you of course need to actually test those model stars, those calculations, with real measurements, with actual measurements of the mass and the radius of temperature of stars that are out there in space. Now, the other thing that we do very often with stars is to interpolate the properties of stars based on the limited sample that we actually have real actual measurements for. Now, this is something that's kind of a dirty secret in astronomy, is that when you look up information for a star, chances are you can probably do a Google search on any star that you want to, and it'll bring up information about the mass and the temperature and the radius of that star. But for the majority of the stars that are out there, direct measurements of the temperature, the radius, or the mass have not actually been made. In reality, there's only about 260 or so stars that have precise measurements of their mass and their temperature and the radius. And by precise, I mean we know those values to about 2%. And really, it's from those values that we kind of try to interpolate the mass and the temperature and the radius of other stars that we measure, based on the limited properties that we can get from just basic observations. And so the point of my talk here is that binaries are what really provide us with these precise measurements of mass and temperature and radius, and we use those binaries in order to interpolate the information that we know about a lot of other stars out there. And so in either case, whether we're using theoretical mathematical models or whether we're using that interpolation method, we need more direct measurements of these stellar parameters, especially for stars that are more massive than the sun. And that's because more massive stars are rare, even though they contribute a lot more to some of the interesting astronomical phenomenon that happens out there. And so this is where binary stars come to the rescue. Binary stars are the key to determining the mass of stars, direct measurements of the mass, precise measurements of the mass, but they also provide a lot of other properties. And so in case you don't know what a binary star is when you have two stars or more stars in orbit with one another. Our sun is not a binary star, and so it's a star that's by itself. And it actually turns out the majority of stars that are out there in our galaxy typically come in a binary system. Now, I mentioned the Big Dipper just a second ago. The kink in the handle of the Big Dipper is actually two stars together. And if you have decent eyesight, you can go outside at night and take a good long stare at the kink in the handle of the Big Dipper. And if you've got pretty good eyesight, you should be able to see that it's actually two stars that are right next to each other. These stars are called Mizar and Alcor. And it's still debatable whether Mizar and Alcor are actually a binary or whether they just happen to be two stars that are close to each other in the sky, but not necessarily gravitationally associated with each other. But the really cool thing is that if you zoom in a little bit more, you can actually see that Mizar itself is broken up into two stars, Mizar A and Mizar B, that orbit around each other as a binary. Now, even more exciting is that if you not necessarily use a different, bigger telescope, but if you use different methods to measure the properties of these stars, you discover that Mizar A is actually a binary pair, 2 stars orbiting one another. Mizar B is a binary pair with 2 stars orbiting each other. And then each pair orbits the other pair. And so you have a 4-star system. And Alcor itself, actually, over there is also a binary as well. And so binaries exist quite a few, there's quite a few binaries out there. And if you want to go outside and you got a clear night and look at the kink in the handle of the Big Dipper, you can actually realize that there's a lot more stars there than what you expect. And of course, if you're a Star Wars fan and you want to know what binaries are, well, it's the type of star system that Tatooine orbits if you want to, stare off into that very dramatic sunset. So why are eclipsing binaries so important? So we mentioned binaries just as a general category of 2 stars in orbit around each other. A binary system, an eclipsing binary, is where you have the 2 stars in such a configuration compared to our location here on Earth that they pass in front of one another, producing an eclipse. And so just like the moon passes in front of the sun in order to produce an eclipse here on Earth, you can have 2 stars in orbit around each other, and when one passes in front of the other, you get an eclipse of sorts. Now keep in mind that these stars are so far away that they actually look like a single point of light in the sky, but you can still measure the brightness of both stars together from that one single dot. Eclipsing binaries are important because they can give us the individual masses, the radii, the temperature of the stars, the tilt of the system, how separated the stars are, if the stars are actually stretched due to the effects of each other's tidal forces, tidal gravity, the distance to the system, and also the age of the stars themselves. A lot of information that you can get from a single star, a single system. We typically need 2 types of measurements in order to really get information from these eclipsing binaries. And the 2 types of measurements are usually referred to as photometry, which is just measurement of brightness of the object over time. And we use that to produce a graph that we call a light curve. In the right, we see the image of 2 stars in orbit around each other, or technically this looks like just 1 star in orbit around the other. But the graph that you see underneath there is what we call a light curve. And it's showing that when 1 star passes behind the other, you get a dip in the brightness because you are blocking the light from one of those stars. Also notice that the blue star is technically the hotter star, and the red star is the cooler star. And hotter stars produce a whole lot more light than cooler stars. And when the blue star dips below the red star, you get a deep dip in the light curve. And when the blue star is blocking out some of the red star's light, you get a shallower dip. And that's because the temperature difference between the stars. The importance of photometry is that using these light curves, we can actually get detailed measurements of the radius of the stars, the size of the stars compared to one another, and the temperatures of the stars compared to one another. We just said that the depths of the eclipses give us a measurement of the temperature of the stars. The shapes of the dips give us an indication of the radii of the stars. And so, for example, if you have a flat-bottomed light curve, as we see here in the middle, that's an example of where 1 star is significantly smaller than the other and gets completely encompassed or completely hidden behind one of the stars during the eclipse. If they're similar in size, you'll get a slightly different curve where there won't be a flat bottom. And the inclination of the system, the tilt of the system, can also change the shape. And so all this information can come out from this light curves, how the systems are tilted relative to each other, whether one is distorted by the other's gravity, the size, the temperature, all that information. Now, the other type of measurement that we need for eclipsing binaries is called spectroscopy, where we're measuring the spectrum, the lines in the spectrum of the star. And that's where you take the light from the star and break it up with a prism or a grating to get a rainbow of colors. And these are used to produce what are called radial velocity curves, which tell us about the motion of the stars. Now, just a little brief review on spectroscopy and how we use this to find motion. Most people have experienced the Doppler effect with sound, the idea that when something is emitting sound and it's moving towards you, you hear an increase in pitch, and then when it's moving away from you, you hear a decrease in pitch. A common example is when you hear that ambulance siren coming towards you and then moving away from you. That same effect applies to light, but instead of changing how we hear the sound, it actually changes how we view the light. Objects moving towards us appear bluer or blue shifted, and objects moving farther away from us appear red shifted. We usually don't see an overall color change in the object, but what we do see is a motion in what we call the absorption lines of the stars. Now, whenever you take light from a star and you break it up into its component colors with a prism or a grating, you see the full rainbow of colors, but you also see these dark lines, this almost barcode show up in the star spectrum. There's a whole lot of information that's contained in that barcode. One of the main things that we get from it is the different types of elements that are made up, that make up that star. But another important thing regarding the motion of the star is the idea that that Doppler shift will apply to those lines, such that when one star is moving towards us, its light becomes blue shifted, its lines become blue shifted and move towards the blue end of the spectrum. And when the other star is moving away from us, its lines become red shifted and move towards the red end of the spectrum. And the very important part is the amount that they shift, how much they shift as they go towards and away from us, is directly related to the velocity of the stars. And this allows us to measure the velocity of the stars over time and produce that radial velocity curve that I mentioned just a second ago. And so this shows the radial velocity curves for two different stars as they orbit around each other, sometimes moving towards us and sometimes moving away from us as they go around and around each other. And that's just based on those lines shifting back and forth. The reason that this is important is because just like on a seesaw, if you think about a seesaw and you've got one person, say an adult on one end and a child on the other, the adult is going to have to be near the center of the seesaw in order to create a balance. The same is true for two stars that are going around each other. And in that case, you need the more massive star closer to the center of the orbit between the two stars. That also means that the more massive star is going to be moving at slower velocities, whereas the less massive star moves at higher velocities. And so in this case, the star that is moving through bigger swings in its motion is the less massive star, star B in this case, and the more massive star is star A. And so this spectroscopic information can give us information about the masses of the stars. Now the key is that if you take the photometric observations, the light curves, the brightness changes over time, and you combine them with the spectroscopy, the motion of the stars over time, what you can do is you can create a model of that binary system. And that's what we attempt to do with some of our research. And basically what you do is you have a computer program that goes through a simulations of stars with lots of different properties, or different masses, different radii, different temperatures, different separations, different inclinations. And you run through and say, well, if the star system existed with these parameters, what light curve would it produce and what spectroscopic radial velocity curve would it produce? You test that, see how well it fits. You test another set of parameters and another, until you find a model that fits the data that you have made observations of. And you can actually see what this star system is like in terms of the mass of the two stars, the radii, the temperature, and all the other properties. Now, it's important to remember that we're kind of entering a new age in astronomy. In addition to some of the larger telescopes that were mentioned, the space telescopes and ground-based telescopes that were mentioned earlier, this is also becoming the era of big telescopic surveys. And so survey telescopes basically aren't designed to look at one specific target at a time. They're meant to look at giant patches of the sky and measure, say, the brightness of many, many stars all at once and be able to gather immense amount of data in a relatively short amount of time. In fact, you can actually go through and say that based on the telescopic surveys that are about to come online, that there'll be more data collected over the next 10 years than probably gathered through all of astronomical history. And that's a really exciting time because that means that there's going to be a lot more candidates that are available for these kinds of studies. One thing that these survey telescopes are very, very good at finding is things like eclipsing binaries, but they're just finding them, they're just identifying them. They're not necessarily doing detailed studies on them. And that's where the role of small observatories can come into play. And so we have a small observatory here at Thomas More University, small aperture telescopes, about 10-inch telescopes. The largest we have is a 14-inch telescope. But the nice thing is that a lot of these eclipsing binary systems are actually quite bright, and that makes them ideal for small aperture telescopes. So small observatories can do this, and even amateur astronomers can do these types of observations if they have the right filters. And so the surveys are going to be really good at identifying eclipsing binary targets for us to study. And then we can do intense photometric observations of them in order to kind of get more precise measurements of things like mass and temperature and radius. Of course, the other thing that we need is partnership for spectroscopic observations. And so we still do rely on some larger telescopes for the spectroscopic data. But these kind of partnerships are things that will be vital for finding out more detailed information about these stellar parameters. And again, it's not necessarily glorious work. It's not necessarily the sexy work for astronomy, but one of the things that's important is to make sure that we've got our calibrations right for a lot of the other relationships that we've discovered. And finding these basic stellar properties is something that's very important towards that. So thank you very much, and let me know if you've got any questions.
Thank you so much, Wes. That was a great talk. And I actually did have a question relating to one of those last things that you had mentioned there, because I thought one of the most interesting things that you pointed out was that I guess, sort of direct observations we have of the mass or the temperature of a lot of stars. I didn't realize it was such a small amount of objects that we have real, physical measurements of that. And so I was curious if you could discuss, are there sort of like propagations of errors that might come out because we don't, fully know, exactly how the models of these stars might work. Maybe this is that have impact on variable stars that set the distance ladder, that set the Hubble constant, that go on so forth and so on with that. So is there anything interesting in regards to maybe errors that might propagate in things we don't 100% know about stars?
I think, that's really the main focus here, is that we don't have that information. And it's especially, like I mentioned, for more massive stars. More massive stars, there's just a real lack of data for the direct measurements. And eclipsing binaries are really the main way, probably the easiest way of doing it. The other way that you might do these kind of measurements is things like interferometry, where you can get direct measurements of the size of stars. But then that's still a very, very limited sample as well. And so, just like Rachel mentioned, and you just mentioned with the distance ladder scale, so many rungs of that distance ladder scale depend on the properties of stars. And not having direct measurements of all those properties, especially for the more massive ones, which tend to be the ones that are more important for the distance ladder, is kind of a big problem. And so it could lead to calibration problems on down the road.
Nice. Okay, cool. Very interesting. Another question then is that in regards to, so it turns out that, I don't know if is it the majority of stars are in binary star systems, or at least a good amount of them are in at least multi-star systems, right?
The last I'd heard, I thought it was majority. But somebody might correct me on that, but I'm pretty sure it is, at least a significant number that are in binary systems.
Okay, so then things like in science fiction, for example, Tatooine, or I've recently been reading a book called The Three-Body Problem, that involves, planets around multi-star systems. I was wondering if you can discuss, have any such planets been discovered? What is the sort of stability of those types of planets, and what is the hope for life as we know it maybe existing on objects?
Right. I do know of, there are a handful of planets that have been found in binary systems. And I think they have been found in both situations where you have two widely separated stars that have their own planets. And you even have had a Tatooine-like system found where you have a planet going around a pair of stars. And so they have actually been found. And I know that there have been lots of detailed studies of the kinematics of that kind of system to try to see whether they're stable or not. Initially, people thought that they would be inherently unstable systems. But I think there's been some more recent results that show that you can have at least semi-stable system in that situation. And so, in terms of long-term habitability, whether they could survive billions of years and in that kind of system, that might be kind of doubtful, but at least on smaller timescales, it does appear that it can happen.
Okay, very cool. And actually, so I want to end with, I think we have time for just maybe one more question. And that's in regards to, so the sun is obviously not in a binary star system, right? So why is that the case? Why do certain stars form in binary star systems, whereas the sun, for example, didn't? And was it because it sort of turned on early enough and it blasted away all the other material that may have formed a star next to it? Or what's the deal with why we don't have another star?
I think, the formation process is not necessarily my expertise, but I think more than anything, it's an act of kind of random chance. Stars don't form, in isolation. Stars usually form from, a really, really, really large cloud of gas that can form hundreds or even thousands of stars at a time. And of that large cloud, and those thousands of stars that form, some are going to be binaries and some are going to be single stars. And I think it's more just a matter of the conditions right around that local area where that star is formed, whether you get a pair or whether you don't.
Okay, cool. Well, unfortunately, we don't have any more time for questions, but this is a great presentation, and thank you so much for offering to volunteer to speak with us. It was a great talk for sure. And so we're actually, sorry. So we're going to end the night with, first, I just want to thank everyone for sticking around. I know I went a little bit over time, but that's okay. We're just here enjoying some beers and talking about astronomy, right? So that's okay to go a little bit over time. We're going to end by going over the trivia and to see how you guys did on each of the trivia questions. So just as another reminder, we're trying to collect donations for the Charlottesville Community Fund to sort of alleviate the effects in the Charlottesville community of COVID-19. So if you have some money to be able to donate, that would be much appreciated. But let's go ahead and go through the trivia questions. So question 1. In the Northern Hemisphere, which of the following happens at the start of spring? That is that the days get longer, but at a slower rate. And so you might notice that in respect to how much daylight there is over the course of a day. Seasons on Earth don't depend on the Earth-Sun distance, but the difference between Earth's closest and furthest approaches from the Sun is about 5 million kilometers. The Earth's located about 93 million kilometers away from the Sun on average. So even still, 5 million kilometers is a small percentage of the deviation of the Earth's orbit from circularity. Springs, how high could you jump on Pluto's surface? That'd be about 25 feet. And that's because Pluto's gravity, surface gravity, is about 1/12 the surface gravity of the Earth. And so that means that if a 200-pound person were to be on Pluto, I think they'd weigh about 16 pounds or so, if I'm doing that math correct, off the top of my head. Let me just look towards the chat. 93 million miles, not kilometers. Thank you for pointing it out to me. Yes, 93 million miles is the one I always remind myself of. Appreciate that. If seasons on Pluto were the same fraction of its orbit on the Earth, how long would spring last on Pluto? That'd be 62 years. That's because the length of a year on Pluto is about 250 years, as was given in our Facebook trivia hint. How long does spring last in the Northern Hemisphere of Mars? It's about 7 months. And so kind of similar to what we experience on the Earth. And then which of the following events happens every Martian year during the Martian Spring? And that's the carbon dioxide poles sort of sublimate from its surface, revealing other things underneath it. Just like the moon is tidally locked to the Earth, a planet could be tidally locked to its star. How would that object experience spring? And that's, we wouldn't have seasons. If one face of the Earth was turned towards the sun, we wouldn't really have seasons in the way that we think about them, because it's all dependent on how much daylight or how much sunlight we are getting on the surface of the Earth. How is the date of Easter determined in the Gregorian calendar? That is at the first Sunday after the first full moon after the vernal equinox, which is why Easter appeared when it did this year. What are spring tides? These are the first high tide after a new or full moon. And so they correspond to the gravity of the sun and the moon, the geometry of those two things working in such a way to create what we call spring tides. During quarter moons, we call them neap tides. Additionally, which astronaut spent the most consecutive time in space? That is Valery Polyakov, which I believe it was over a year, 14 months in space he spent in a single mission. So pretty wild stuff. So hopefully you guys did okay on the trivia. 438 days. Okay, cool. So 438 days specifically in space. So hopefully you guys did well. Hopefully you guys liked it. Let us know if you thought anything was interesting in regards to the trivia specifically. And finally, so we're going to wrap up the night. As usual, we love to get feedback on things that we can improve for future Astronomy on Tap events. We're going to have probably a couple more virtual events going forward. but we'll soon be going to in-person events, hopefully. But if you have any feedback you'd like to provide to us to make this event as great as possible for you guys, please let us know on the feedback form that hopefully is just the actual Google form and not the internal form that I use to help edit the feedback forms. And finally, if you guys grab that link, I just want to give thanks to everyone that's helped out tonight, the speakers, Geoff, Rachel, Wes, the volunteers, Ed, Molly, Jacob, Katerina, and then of course the organizers. Of course, I got to thank myself, Catherine, Brett, Marilyn, Whitney, and Scott. And then finally, thanks to all of you that make putting events like these on actually worth it, making it fun. Make sure to check us out on Facebook or Twitter if you guys want to see future events and more fun astronomy content. But for now, as usual, I just want to thank you all for joining us, and cheers you guys as I say goodbye to another fun Astronomy on Tap event. It was great seeing everyone and hanging out and talking about astronomy. See you next time.